Hi everyone, this is going to be a lesson about matrices and systems of linear equations. So in the past two lessons, we've been talking about systems of linear equations. We had a lesson where we did small problems, where there were two equations and two variables. And then we had a lesson where we had three equations and three variables. So in this lesson, we're going to continue to solve systems, but we're going to do them in a little bit of a different way using matrices. And we need to talk about what that means. So let's go ahead and get started. Okay, matrices and systems of linear equations. I guess I should say, I don't know if I've said this yet, but some of you may have seen some of this stuff in an algebra class before. So if you've seen it, then you can consider it review. We might go a little bit deeper into it over the course of this lesson and the next lesson. If you haven't seen it, then that's okay too. We're going to give a definition here and say a matrix. A matrix is a rectangular array of numbers. And the plural form, when you have more than one of these, you call them matrices. When you have more than one matrix. Some examples, just quick examples of matrices. These are not really problems for us. They're just objects. Let's see. This rectangular array of numbers, 2, -3, 1, 0, 4, 5. And we put square brackets around it. That's one example of a matrix. We say rectangular array of numbers. You could think of it as a rectangular grid of numbers, but it's kind of altogether going to be treated as just one object. It's a collection of numbers. And then you could also have a rectangle that's sort of taller. So maybe 3, 1/2, -2/3, 0, 5, 5. That's also a rectangular array of numbers. It also has the square brackets around it. You know, in math, we use square brackets sometimes for intervals, but this is totally different. This is square brackets being used just to kind of show us where the matrix begins and where it ends, you know, to contain all of the numbers in the grid. And you see that it contains real numbers. They can be fractions, they can be positive or negative, they can be 0. You could have the same number repeated twice. Yeah, so that's what a matrix is. What does this have to do with systems? So systems and matrices. If we are given a system, and in this class we're talking right now about systems of linear equations, so maybe something like this. You know, linear equations kind of fit this form. They don't have any x squareds or square roots or trig functions or exponentials or anything weird like that. Everything is nice and flat, straight lines, flat planes. That's kind of what it means to be linear. Now, if we're given a system like this, we could talk about solving it, but what I want to say is when you look at this system, and when you look at systems in general, like these 3x3 systems we've been looking at that have 3 equations and 3 variables, you know, there's kind of a column of x's, a column of y's, a column of z's, a column of the right-hand side. Really, this thing looks like a rectangular grid. And what really makes one system different from another are the numbers that appear in front of x, in front of y, in front of z, and what numbers appear on the right-hand side. What we're going to say is we can write a matrix based on the system. where I'm going to sort of extract all of those numbers. The numbers in front of the x's, the number in front of the y's, the numbers in front of the z's, and the right-hand side numbers. So the numbers in front of the x's, well, there's no number written in front of x here, but you would think, it's not a 0. It's not 0x. There's one copy of x here. So if there were a number in front of x, it would be a 1. I'll go down this column first. We get 1, 1, 3 as sort of the numbers in front of the x's. The numbers in front of the y's are -1 to -1. The numbers in front of the z's are 3, -2, 5. And the numbers on the right-hand side are 4, 10, 14. And we don't write anything else. We don't put the equal signs. We don't put the plus signs. We don't put the little squiggly bracket on the left side. And we don't write the x, y, or z. We just extracted all the numbers. And this is known as the augmented matrix of the system. And really, what this matrix does is it sort of captures all the important information about the system, because we know that every problem that we saw in the previous lesson was kind of in this form. It always had a column of x's, a column of y's, a column of z's. So we would always write x's and y's and z's and equal signs. But really, if every problem fits that same format, then maybe we could just write it as a matrix. If we write it as a matrix, it sort of saves us a little bit of time because we don't have to write x's and y's and z's and equal signs. You just write the numbers that sort of determine the system. Besides saving us a little bit of writing, I'm going to say that to solve the system, we can perform Gaussian elimination on the equations, or on the augmented matrix. And I'll show you how. I'll show you how we do this to the augmented matrix. I guess an idea to keep in mind is that if we have 3 equations, then the matrix is going to have 3 rows. So each row represents an equation. And if we have 3 variables, well, there are going to be 4 columns because we also need that column for the right-hand side. By the way, in case you're wondering, what does this word augmented mean? Like, why don't we just call this the matrix of the system? Why do we have this extra word? Augmented means that the matrix includes the right-hand side. That's all it means. And in this class, whenever we do a matrix for a system, it's always going to be the augmented matrix. So the right-hand side, technically that's what makes it augmented. But we need the right-hand side. If you didn't write the right-hand side, then you wouldn't really have all of the information of the system. And you know that when we do Gaussian elimination steps, like we did in the previous lesson, they happen to the left-hand side and to the right-hand side. So we need that. All right, so I'm going to show you, let's solve this. Let's solve this system, but I'm going to show you how we could solve it working with matrices. Now, in the previous lesson, we would have solved this system by working with these equations. We would have said, all right, we need to kind of get this in triangular form. We need to add multiples of equations to other equations and try to like get some of these spots to be kind of blank spots. Well, you could think of the same thing with this matrix, but instead of adding a multiple of an equation to another equation, we're going to add a multiple of a row to another row. Instead of multiplying an equation by a constant, we're going to multiply a row by a constant. And instead of interchanging equations, we might interchange rows. So I'll show you. Let's copy that augmented matrix down again, because we're going to work with it. So you know how last time when we were doing this process, we would kind of write the system and then draw an arrow pointing to the system we get after doing a step. We're going to do that here, but with matrices. Now, you could think, like, what would triangular form look like? Like, what would a augmented matrix look like that sort of corresponds to a triangular system? Well, we kind of want the lower left entries to be zeros, right? Because you want, in the system, you want, instead of a 3x, you want like a 0x. So we want the lower left entries to become zeros. That's what it would be to get this to be triangular. And then you think, well, what steps do I need to do to get rid of this 1 and this 3 and this -1 to turn them into zeros? We're still thinking the same way we did in the previous lesson. I am going to add -1 times row 1 to row 2. By doing that, row 1 itself is not changing. Row 3 is not changing, so I'm just going to copy it down. Row 2 is getting something added to it. So let's see. -1 times 1 gets added to 1. You get a 0 here. That's what we wanted. That's why I did that step. I think this is going to make us one step closer to triangular. But we also have to do it to all the other numbers in the row. So -1 times -1 is 1, which gets added to 2. So I get a 3 here. -1 times 3 is -3. It gets added to -2 to get me -5. -1 times 4 is -4, which gets added to 10 to get me 6. And that was one step. And, you know, you saw that in the previous lesson that sometimes these take 4 or 5 steps to get into triangular form. And that's still going to happen here. It's still going to take 4 or 5 steps. So it's not saving us steps, but it's nice to write this way because there's a little bit less writing instead of X's and Y's and Z's. Let's see. I really would like to get rid of this 3 in the lower left. I think if that was a 0, that would also help us. So in order to make that a 0, I'm going to add -3 times row 1. You know what? Maybe we can abbreviate. Instead of row 1, sometimes we call it R1, if you want to do that. And I'm adding it to R3. I think I said last time that, you know, if you want to abbreviate it differently for me, that's fine. So row 1 and 2 are not changing, so let's just copy them down. And we get a 0 here. That's what we wanted. What happens to the rest of it? So -3 times -1 is +3. It gets added to the -1 that was here and becomes 2. -3 times 3 is -9. It gets added to the 5 that was here to get me -4. -3 times 4 is -12. It gets added to the 14 that was here to get me 2. And we're almost in triangular form. Let's see. Let's see, how should we do this? So it would be nice if we could get rid of this 2. You know what might make things easier? I noticed that everything in the third row is a multiple of 2. And we're allowed to multiply a row by a constant. So what we could do is multiply row 3 by 1/2. I think that's going to make this a little simpler. So let's do that. I mean, I wouldn't always multiply row by 1/2, but if you notice that everything is like a 2 and a 4 and a 6 and an 8, you know, yeah, that made this a little simpler. So let's see. Can I get that 1? Can I get rid of that 1? Right, to get this to be triangular, I'm imagining the triangular shape like we did last time, the right triangle. And the only thing that's stopping us from doing that is this 1 that's here that I'm pointing at. I want that to be a 0. So should I use a multiple of row 2? Should I do like negative 1/3 of row 2 getting added to row 3? That's one option. We could do that. It would make a 0 here, but then I would have to deal with like negative 1/3 times -5 and adding that. I'd rather not deal with fractions if I don't have to. And there is another way that I could do this. What if, instead of getting rid of this 1, we get rid of this 3, turn this into a 0, and then just interchange rows afterwards? That would also get triangular form. So I'm going to work on getting rid of the 3 that's here. And to do that, I'm going to add negative 3 times row 3 to row 2. Either way would work. But you see, if I knock out this 3 instead, I think it's, I don't know, feels easier to me. Maybe it's just a matter of preference. All right, so let's copy down row 3 because that's not changing. We're adding something to row 2. All right, so negative 3 times negative 2 is positive 6, getting added to the negative 5 that was already there to become 1. Negative 3 times 1 is negative 3, gets added to the 6 that was there to become 3. And now I'm going to do my idea of interchange rows. Just like in the previous lesson when we interchanged equations, well, each row represents an equation, so we can interchange rows. 0, 0, 1, 3. This is triangular form. This represents a system in triangular form. Okay, so this matrix represents a system in triangular form. And I'm going to show you the system. I don't have to write it, but because this is kind of new to us, I'm going to. Earlier, I wrote a system at the beginning of all this, and then I said we can write a matrix based on the system. We turned it into this matrix, and then we've been working with matrices ever since. But you can also go back from a matrix to a system. If you think about what do these numbers represent? Well, row 1 represents equation 1. 1, negative 1, 3, those are the numbers that appear in front of x, y, and z. The 4 is the right-hand side. In equation 2, or row 2, the 0, 1, and negative 2, they represent the numbers in front of x, y, and z, and the 1 is on the right-hand side. And in row 3, 0, 0, 1 represents 0x plus 0y plus 1z equals 3. So maybe writing it like this helps you see that, yes, we did get triangular form. And we use back substitution now, right? You say, to finish solving, equation 3. Do you want to call it equation 3, or do you want to say we're just getting this from row 3? Well, either way, z is 3. Equation 2, y minus 2 times 3 equals 1, so y equals 7. equation 1, which we get from row 1, tells us x minus 7 plus 3 times 3 equals 4. Minus 7 plus 9. All right, so this gets us x equals 2. So the solution to the system, we found one unique solution this time. That seems to be a pretty common outcome. 2, 7, 3. So working with matrices like this has its advantages. It's kind of like we strip down the system down to the essential components, the numbers that are what actually matter, and then we can just work with rows of numbers and adding rows of numbers to each other. And maybe if a system was even larger, then you'd have a larger matrix, and it would be really nice to just work with numbers instead of lots of x's and y's and z's and equal signs and pluses and all that. Matrices actually have a lot of uses. This is one of them. We're going to talk about matrices a little more in an upcoming lesson, I think. So let me talk a little bit about different forms that matrices can be in. There's a form that's called row echelon form. So we did, just to recap, we started with this augmented matrix of a system that looked like this. And we performed a bunch of steps on it, which I'm going to summarize by saying that we did Gaussian elimination, right? In the previous lesson, we described it as 3 steps that you're allowed to do to equations. And now I'm saying you're allowed to do those 3 steps to rows. Like adding a multiple row to another row, so on. We did that and we wound up with this. Zero, 0, 1, 3. Let's move this up. And the matrix that we got, this matrix, is considered simpler because we can quickly get the solutions from it. Solutions might be singular or plural, right? Actually, there might be no solutions to a linear system. But the point is, once you get an augmented matrix that corresponds to a triangular system, like this one does, that's considered to be the form that we want. Here, I have a definition for you. Definition: the leading entry. The leading entry of a row is the first non-zero number when reading from left to right. So, if I say it's the first, I have to explain the first in what sense. It's the first as you go from left to right. So, for example, in the sort of simpler form that we got this to, I would say that in row 1, the leading entry is this 1. In row 2, the leading entry is this 1 over here. And in row 3, the leading entry is this one over here. It's the first non-zero number. By the way, this word entry, we might refer to the numbers that are in a matrix as the entries of the matrix. This happens to be the leading entry of each row. So, now I can tell you about row echelon form. Matrices that result from Gaussian elimination are in row echelon form. And row echelon form could be described as having two properties. First of all, the leading entry of each row is to the right of the leading entry in the row above it. And one other thing. There's one other thing, but maybe I should say something about this sentence. The leading entry of each row is to the right of the leading entry in the row above it. That's really like kind of wordy, but can we decipher what that means? Well, maybe just look at this one up here. How about this? How about I circle the leading entries? We're talking about leading entries a lot. So there's this one, there's this one, and there's this one. Do you see that each leading entry is to the right of the one in the row above it? So it's sort of like as you go down and right, down and right. If this matrix were larger, you would keep going down and right, down and right, down and right. Actually, that's what gives it the triangular shape. So this sentence is kind of describing that you go down and right. That's what makes it triangular. Besides thinking of it as triangular, you could also think of it as like a staircase. So I'm going to draw this kind of staircase pattern that we're getting. See that? In fact, I believe the word echelon sort of translates from a word that means step. Something like that. So yeah, it's like a staircase pattern or a triangular pattern. There's one other thing I said, though. I should get to the one other thing. Well, besides having that triangular or staircase shape, what else would a matrix need in order to be considered row echelon form? And there's one other thing. All rows consisting entirely of zeros, if there are any, are at the bottom. Okay, so that did not happen in this example above. We didn't have any rows consisting entirely of zeros. I guess if you did, there would be no leading entry in that row because there'd be no non-zero number. But yeah, so if we had a row that was all zeros, we would need it to be at the bottom, but we're allowed to interchange the positions of rows. So if you had a row in the middle that was all zeros, you would just interchange rows to move it to the bottom. So technically you need to do that if that comes up. But mainly I think it's this first, this is kind of the bigger deal, is getting that triangular shape. So Gaussian elimination, we know, gets us something that's triangular, and then we can use back substitution to get the solutions. And I'd like us to do some more examples. Let's see. I think before we do that, there's something else I want to discuss. So I said that was row echelon form. There's also something called reduced row echelon form. And the idea is that we can modify the matrix further to make it even simpler. Well, this will be a definition. A matrix is in reduced row echelon form and that is sometimes abbreviated as RREF. Actually, it's usually, when you abbreviate RREF, it's usually all lowercase. That's usually how I see it. So interesting that it gets abbreviated to all lowercase. But anyway, reduced row echelon form if we modified it to satisfy the following additional requirements. So additional requirements means it has the same two requirements above plus a little more. Just two more things. By the way, when I say modify it, like we're going to modify the matrix, it's still with those same steps, the same adding a multiple of a row to another row, multiplying a row by a constant, or interchanging rows. You want to get these additional properties. First, each leading entry is 1, must be 1. Some matrices that are in row echelon form have this, and some of them don't. Actually, the example that we did above did have this property, but there's a second property, and that is every number above and below each leading entry is 0. Okay, now the row echelon form matrix that we wrote above does not satisfy this last property. So it is not in reduced row echelon form. I'll show you real quick. Here's the matrix from earlier. I circled the leading entries, and you can see that, the numbers below the leading entries are zeros, but this says that we would also need to have the things above the leading entries be zeros, and that would be considered even simpler. And I'm going to show you what that looks like. Let's do it. Let's start with that matrix. So 1, -1, 3, 4. Let's say we were solving that system. We got to this matrix that represents a triangular system, also known as row echelon form. And let's say we would like to get this to reduced row echelon form. We keep working with it. We need to get more zeros. We need to get like this -1 to be a 0, this 3 to be a 0, this -2 to be a 0. We can't just replace them with zeros, though. We have to do those 3 steps that we're allowed to do to rows. So I'm going to add 2 times row 3 to row 2. Before I do it, do you see why I'm doing that? Do you see what that's going to do? Well, it's not changing row 1, so let's just copy row 1. It's also not changing row 3. Sometimes I like to write the ones first that are not changing. But we're doing something to row 2. So 0 gets added to 0, so that's still a 0. 0 gets added to 1, so that's still a 1. 2 times 1 is 2, and it gets added to negative 2 to give me a 0 here. That's the reason I did that step, because I need the numbers above the leading entry to be zeros also. And finally, 2 times 3 is 6, and that gets added to 1, so I get a 7 here. Next, we need to get more things to be zeros. How about we add 1 times row 2 to row 1. You know, I think earlier we weren't really changing row 1, but now I want to change it because it needs some zeros in it. So that's going to, well, I guess we'll write row 2 and 3 first. All right, now, what does it do to row 1? The 1 is still a 1 because it gets 0 added to it. And then we get 1 gets added to negative 1. That's the reason why I did that step, was to turn this thing into a 0. 0 gets added to 3, so that's still a 3. And then 7 gets added to 4, so that becomes 11. We need one more step. One more step, because this property says every number above and below each leading entry. So that 3 that's floating around up there, that also needs to be a 0. So we need to figure out, like, I guess we need a multiple of row 3, right? So how about we add negative 3 times row 3 to row 1. I think that's going to do it. So I'll copy the rows that are not changing. And row 1 is the one that's getting something added to it. So the 1 gets 0 added to it. The 0 gets 0 added to it. The 3 gets negative 3 added to it. That's what we wanted. But then what happens to the 11? Negative 9 gets added to 11. You get 273. So you might say, like, well, why are we going through all this extra work? What's so good about... I'll say this is in reduced row echelon form. This is reduced. And what's so good about this? Do you see something that's good about this? I'm going to actually go back to the page earlier where we solved this system, where we did back substitution. Look at that. That's the solution that we found. Look at the reduced row echelon form. 273. It's right there in the matrix. And that wound up being the solution. But look at all this substitution work we did. Maybe it wasn't that bad, but we, looked at equation 3, equation 2, we had to substitute something in. Equation 1, we had to add and do some arithmetic to get the 273. But now the 273 is right there staring at us. So from this form, we can immediately get the solution. No back substitution required. You just look at it from top to bottom. Now, why is that? Why does the vertical 273 mean that that's the solution? It's because if you think about what system does this matrix represent, it's basically saying 1x plus 0y plus 0z. Just 1x equals 2. 1y equals 7. 1z equals 3. So it's telling us x, y, and z. Cool, so that is sort of the nice thing about reduced row echelon form, is the answer just jumps right out at you and you don't have to do any kind of substitution. I have a little terminology thing to tell you. It's going to be one thing that we already know and then one thing that's new. So the process of converting a matrix to row echelon form is You know what this is. This is Gaussian elimination. All right, so that's the one that we already know the name of. The process of converting a matrix to reduced row echelon form. That's where you do Gaussian elimination, but then you keep going and you go further. You reduce it further. It is called Gauss-Jordan elimination. Gauss-Jordan elimination. I guess at this point, I want to tell you that we've been doing a lot of examples in the previous lesson and this one that have 3 equations and 3 variables, but everything we're saying also works for systems of other sizes too. So, for example, 2 lessons ago, we focused on systems of 2 equations. And all of this still works if you have 2 equations, 2 variables. So let's do an example like that. So I have a 2x2 example and a 3x3 example. Well, let's do the 2x2. Let's say we're given the system. I'm going to ask you to try this, I think. Yeah, this is a pretty small one. All right, here is the system. Don't solve it yet, because I have to write the whole thing. So the instructions are going to be, I want you to write the augmented matrix for the system and use Gaussian elimination or Gauss-Jordan elimination. Your choice. To find all solutions. Okay, that's what I wanted to say. So I'd like you to pause the video and try this. So this should be quicker than the 3x3 example that we've been doing. This would be called a 2x2 system because there's two equations and 2 variables. So what I wanted you to do is find that the augmented matrix must be 2, 4, 6, 3, 7, 12. And then we want to do the steps to this, right? We want to get this to be reduced. And it's your choice if you get it to row echelon form or if you go all the way and do Gauss-Jordan to get it into reduced row echelon form. But remember, there is some flexibility in these steps. So if you do this slightly differently than me, it might be fine. I decided, though, my first step, I said I was going to multiply row 1. Why did I write the 1 like that? Here, row 1. Do you want to write like R with a big one or R with a little one? Either way, I guess. I guess above I was using it as like a little tiny subscript. All right, anyway, I'm multiplying it by 1/2 because I saw 2, a 4, and a 6, and I said, hey, those are all multiples of 2. It would be simpler if I do this. But that's optional. You didn't have to do that step, but I thought it made the system a little simpler. And now I'm thinking about getting some zeros to show up. So I decided to add -3 times row 1 to row 2. Row 1 is not changing. Row 3 gets, I'm sorry, not row 3, but row 2 gets a 0 in place of that 3. because we added -3 to 3. We also have to say -3 times 2 is -6. It gets added to 7 and becomes 1. -3 times 3 is -9. Gets added to 12 to become 3. At this point, we already have finished Gaussian elimination because this is row echelon form. It's not reduced row echelon form, though. But you could work with this. You could do back substitution from here to find the answer. But I decided this is a small enough problem, and I said, you know what? I think we're like one step away from finishing Gauss-Jordan elimination. So I decided that I was going to add -2 times row 2 to row 1. And that got me 1, 0, -3, and row 2 did not change. This one is in reduced row echelon form. And the nice thing about this is I can see the answer. It's -3, 3, right? The solution is -3, 3. Or remember, you can also write it as x equals -3, y equals 3. I got that from this. Oh, by the way that this problem was phrased, hold on a second, how is this phrased? Look at this, it was a whole lot of words. Write the augmented matrix for the system and use Gaussian elimination, blah, 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 blah. Okay, so from now on, when I want to ask you that kind of problem, I might just say, solve the system using matrices, or something like that. So if you see a problem that says solve the system using matrices, it means do steps like this. By the way, another little terminology thing. Overall, this process is sometimes called row reduction. So we might say that we are performing row reduction steps in order to get row echelon form and reduced row echelon form. That's just like a little side note in case you hear me use that word. If I say that we are row reducing the matrix, it's just these kinds of steps that we're doing. By the way, if you want to also mention this in the terminology, these steps that we're doing are sometimes called row operations. So we performed row operations to reduce the matrix. So that example we just did had 2 equations and 2 variables. I want to have you try one that's 3 equations and 3 variables. So I am going to ask you to use matrices. So the methods from this lesson, don't solve this the way we did in the previous lesson. I want you to write it out with matrices. Use matrices to solve, but it's still going to be given as a list of equations. But you need to find the augmented matrix and then work with that. 2x minus y plus z equals 1. 4x plus y minus z equals 5. X plus y plus z equals 0. So I'd like you to pause the video. This might take a little bit of time, might take a little longer. Try to solve this system using matrices. Okay, so I don't know about you, but this one took me 5 or 6 steps. Well, first of all, we write the augmented matrix, right? So we get the numbers 2, -1, 1, 1, 4, 1, negative 1, 5, 1, 1, 1, 0. And how about this? Let's double check these numbers, because I know that if I got one of these numbers wrong, it's going to throw the whole thing off. So let's just double check. First equation, 2, negative 1, 1. Yeah, first equation, first row looks good. 4, 1, negative 1, 5. Good. Last one, there's 1, 1, 1, and a 0. Good. Okay, that was quick, but it was worth double checking. I decided, and you might decide some other step, but I decided to add negative 4 times row 3 to row 2. You might do a different first step, but I said that that's going to get rid of that 4. Okay, that gets this 4 gone. I wanted that 4 gone. And then it wound up giving me negative 3, negative 5, 5. We need to keep going. But we're one step closer. Really, we're trying to get a lot of zeros in here. Matrices with zeros are always considered simpler. So, next up, well, can we get rid of this 1 down here? It's a little tricky, though, because we would have to do, like, negative a half of row 1. And then what's going to happen to these other entries? They're going to become fractions, which is okay. I mean, a matrix can have fractions in it. That's okay. But remember, in some of the problems we've done, I've shown you little things you can do to avoid fractions sometimes. What if instead of getting rid of this 1, what if we get rid of this 2? And then later we can interchange rows. So I decided to add negative 2 times row 3 to row 1. Yeah, I'm going to get that 2 to become a 0. And then, you know, to get it into, to represent triangular form, we're going to wind up interchanging rows probably. See, a 0 up there is nice. What else do we get? I got negative 3, negative 1, 1. And then I looked for what's my next step. My next step is optional. But I saw this negative 3 and this negative 3, and I thought, you know, those line up really nicely. It's going to be nice if I sort of add one to the other. But I decided to multiply row 1 by negative 1. You might not do that step if you don't want to. You know, do you consider this to be simpler? Maybe it's about the same, but I thought that might help. So now I'm going to add row 1 to row 2. Technically, I'm adding a multiple. You know, you add a multiple of a row to another row, but you could just say I'm adding 1 times row 1 to row 2. So row 1 is not changing. Row 2 is getting something added to it, so row 2 will change. Let's copy row 3. All right, 0 is still 0, and then I got 0, negative 4, 4. Do you see that this is almost triangular form? That all we really need to do is interchange rows? Interchange the positions of rows, change the order of them. So you write 1, 1, 1, 0 as the new row 1. Move this one to be row 2. And move this one to be row 3. So we swapped around the order of rows. We're allowed to do that. This is row echelon form. Not reduced, but row echelon form. It represents a system in triangular form, and it has that nice staircase pattern to it. Negative 4, 4. Do you want to do something about that? Do you want to, like, just because you got it in row echelon form, it doesn't mean you have to stop here. I'm going to go one step further. I'm going to say multiply row 3 by negative 1/4. because that 4 and -4 were bugging me. And I was like, well, that's just 1 and -1. So now we have it representing a triangular system, and we can do back substitution. So what does row 3 tell us? Notice I'm calling it row 3. I'm not calling it equation 3. But as an equation, what would this say? It says 0x plus 0y plus 1z equals -1. Remember, the final column, the last column, represents the right-hand side. So there's kind of like you could imagine an equal sign being here. So there is an equal sign. So yeah, z is -1. Then I move up to row 2. This is substitution, so we'll have to put that -1 in somewhere. Row 2 says 0x plus 3y plus 1z equals -1. So looks like that once you put in the correct thing for z. And 3y equals, add 1 to both sides. 3y is 0, so y is 0. Row 1, I think I'll write over here. Row 1 says 1x plus 1y plus 1z equals 0. Is that okay? That it equals 0? That could be fine. Yeah, it's okay for the right-hand side to be 0. So x plus, well, y is just 0, right? This is just nothing. We're adding 0. Plus z, so that's -1 equals 0. So x is going to be 1. By the way, as we convert the matrix back into equations for these final steps like this, you know how I said that the final column represents the right-hand side? So you can kind of like imagine little equal signs being here. Sometimes when people write an augmented matrix, sometimes people will draw a little line here. This is optional. Maybe it's like a dashed line. You can write that if you want. I typically don't, but that's to kind of separate the left-hand side from the right-hand side. Pretty cool because it helps you see that, you know, these are like X, Y, Z columns, and then this is the right-hand side column. Anyway, we did it. We solved it. My solution, the only solution to this system. Remember, when you find the solution, you need to write it X, Y, Z, even though you usually find it in the opposite order. You need to write X first, then Y, then Z. And that's the solution to that system. By the way, if you decided, you know, this problem said use matrices to solve. So when it said that, it's up to you if you want to do Gaussian elimination or Gauss-Jordan elimination, where you reduce it all the way. In my notes, I actually did both, but I'll tell you that we're finished with the problem. But I'll just say that if you did reduce all the way, it would reduce all the way to this. So you can look at the matrix I have above. You'd be able to reduce it further. You'd get this, and then you would look at the final column, and that would give you X, Y, and Z. So you can do that if you want. This problem didn't say you had to. So I think now, by now we should be getting comfortable with solving systems, both of you know, systems that have 2 variables, 2 equations, or 3 variables, 3 equations. This method would also work for larger problems if they came up. So I think we'll wrap things up here. So, for the past 3 lessons, we've been talking about how to solve systems. And it has led us here. We started with small systems, uh, intersection of two lines, but now it's actually gotten a bit more complicated, right? So, we've had 3 lessons about solving systems. We have learned about matrices. And in the next lesson, we're going to learn some other things that you can do with matrices besides just using them as like the augmented matrix of a system to help us solve a system. Matrices can also be used for other things. So we'll see that coming up soon. All right. So that's it. Take care, and I'll see you soon.